In this video, I'm going to show you how to do basic image corrections. So when you get an image, there are various artifacts. For example, in this image I'm showing you here, there is a specific area where you can see very high grounds. So those are scaling artifacts. So typically when we get an image, we want to flatten this. It's basically to do a line-wise flattening, and because each line, if you see them closely, each line of these, let me show you. I can draw a scaling box so it's illustrate the point better. So you can see that each line, they are at different height levels, so they're not flat. Right? At the top of the image, you see darker, which is lower, and the middle is higher, then it goes lower again. So to correct for those unevenness in the height in each line, we use flatten. And so right now I'm going to do a zero order flattening because it looks like that's what we usually do in the first step. So I wouldn't check mask. So the mask means that whether you want to use mask flattening or not. Basically, what they want to exclude a specific area when you try to fit the flattening equation. So on the right side of the image, it shows you the mask, and the red areas are the mask, which is specified by, you can specify its color here. So you can choose the mask color. You can also choose whether you want to show the mask or not. Right? Click to show the mask and unclick, and discharge the mask. So you can change the level of the mask. So basically what mask means is it's a threshold level. So above the threshold, it's basically below the threshold, it's masked, and above the threshold, it's not masked. So as you see here, anything that's well, actually, I'm saying that in the wrong order. It's actually above the threshold, then it shows the mask. Right now, I have like a 0.3 nanometer mask, so it's specified by this value. So above this level, the image on the right is masked by the red color. So you can change by either typing a number here, or you can also drag this bar there. So as you see, you can use the arrow to fine-tune the mask. You can also use, well, sometimes the arrow is a rough tune. If that's not fine enough, you can right-click the slide bar, and you can change the step size for fine-tuning your sidebar. So you can decide what's the intervals for the adjustment if you click arrows or if you click the empty space in the slide bar. So so right now we are not going to use the mask when we do the zero order flattening. That's just to see what the image, how it needs to be corrected. Right? So yeah, if you check the mask here, it will exclude the region in the masked area. That's colored by red. So those regions, they won't be used in the flattening procedures, but I want to include them. So so I uncheck the mask here. So I do a zero flattening. Just click this one. So I click this button. So what you see is some difference here. So we add a new channel. It's called modified height trace. So this is the new channel, new image that's flattened. That's basically I just did a zero order flattening, and you can go back to the original height trace channel, which you see it's the unmodified channel. So which basically is you see those unevenness in the different y coordinates. But when we go to the modified height trace, which we did the flattening, now we check again. So draw a scaling box. Now it's more even, right? There's no dark regions in the top and the bottom of the image, so everywhere is even. Now here comes this specific area. So you see that area is not flattened well, and we can correct it by several ways. So you can either use a mask flattening. So right now you see that specific area, if you see on the right, that area is masked. So you can basically, what you do is you check the mask box, which means that the area of this specific hide run, it's excluded in the flattening procedure. So once it's excluded, the flattening will take care of the dark lines, so they should be, flattened well. But we don't really care about that. We can leave that as outlier, that particle. So I'm gonna do a ZR flatten again, but this time I masked. Okay, I'll check the mask here box. Yeah, sorry, let's do it. So as you see that, let's try again. So I already used auto scale, so that's why every time it rescales. So after you can keep the same scaling but uncheck auto scale. So I would like to use, that's my typical numbers. The offset is a -1 nanometer and the scale is 4 nanometer. So you see the dark line is gone, so it only leaves this outlier that we don't care, right? But if you do want to take care of even that one, you have to use some kind of filter. So we have several ways. So let's see. So yes, and you can also use, I forgot to add something. So you can also use auto mask. If you check this box, the mask will automatically mask, the optimized mask for you. You may not like it, but you may want to fine-tune the mask. But if you want to go back to quickly, like to mask most of the useful particles, you can just click auto mask, and then you can fine-tune this procedure. So that's what the auto mask means. Yeah, you can, and the other way is to mask this. I'll go to how to remove these artifacts in a couple of minutes. So let's talk about the other ways to mask our particles. So you can use intensity to mask them. Just click the intensity plot, and so you see there's a peak which represents the background of the intensity. So what you do is you can click the zoom, the magnifying glass, and then choose horizontal zoom and drag on the bar. So we just want to focus on this area. So we have these, just zoom in this area. Now you can right click the figure, and then you can place that called data threshold bar. So what this does is it places a bar, that's a green bar, and when you move the green bar, it changes the mask for you. So this is really a fine-tuned procedure. So if you don't want to use, you can so you and I have different ways, right? You can either you move the bar to change the mask. This is a really fine-tuned process. Or you can use the sliders. Or you can just enter the the levels, the mask levels here. Or you can just change the step size and change the individual major and minor steps for the slider. So now you have several ways for masking purpose. And you also have options to place the lower bar and the upper bar. So what this does is interesting. So then once you have done the lower, once you have placed the lower and the upper bound bar, you can make a double density slice either between the two bars, which really means the red and the blue, which you can make a density slice between this red and blue, or you can make a density slice outside of this red and blue. So what does that mean? Let's see. So if I make the density slice between these, basically I only mask the DNA, the molecules that's between these data range. So anything outside of it, anything higher than that, anything lower than that, they are not masks. So let's see if I do a mask between slices. So now you see anything that's below this height is masked, like the background, right? It's it's excluded, and anything that's above that data range, such as these proteins, they are higher than the blue bar there. And so that's why you see the proteins, they are kind of like a halo circle, so they're not completely masked, they only mask the the parameters of it. So so this could be useful for some analysis, and I can do the reverse. You can do mask the density outside of slices, And what that happens is it masks everything outside, like anything lower and anything higher, like the center of the protein, which is higher ground, but anything that's in between, like the DNA and the protein circles, they are not highlighted. So, so this is kind of reverse procedures. All right, to return back, we just click this basically go back. So, okay, so that's for how to mask our protein in our the image. So then let's go back to how to remove these artifacts here. So so to remove that artifact, let me do one thing first. I want to do the it's not threshold, it's not scaled properly. Let's do the drag a scaling box. Distribution take care of things. Yeah, I want to remove that specific spot which has a true line there. So so we typically use medium filters. This is not the typical medium filter you use in other AFM programs. So this one, it has unique advantages in that you can specify the standard deviation. So some basics for filters. So basically you have to specify a region. So what filter means is that it uses its neighborhood of each, if you want to do an operation on one pixel, and if you apply the filter on that specific pixel, what the filter does is it uses the neighboring pixels and to determine what the corrective values for the pixel that you want. So you can specify the neighbors how much neighborhood you want to use, and you can specify the y direction, the x direction. You can use a symmetric neighborhood. You can also use a square box neighborhood. Right now, for this line, the horizontal line, apparently I would only use a vertical neighborhood situation. I set up y-axis, vertical y. I use 7 pixels in the y direction, but I only use 1 neighborhood in the x direction. So that's optimal for fixing horizontal line artifacts. So what's unique about this medium filter here is it also lets you pick up a threshold that it's called the standard deviation. So basically when you so basically what the program does is it takes 7 pixels, right? It specifies 7 pixels along the y direction around the target pixel. Okay, so it takes 7 pixels. It did a calculation of it does a calculation of the average and the standard deviation, and now it calculates. Then it knows which one is outlier or not. So it uses the standard deviation to determine whether it's an outlier or not. So if the specific pixel, like this line, which is pretty high, if it's above 2 standard deviation beyond the average value, then it's gonna remove, right? And so you can specify how far beyond the how many standard deviation beyond your average value that you want the artifacts, that you want them to be classified as artifacts or not. So right now, this is our optimal value. I don't usually change these, but apparently you can optimize for your own needs. So I just click OK. So I would assume that this line artifacts, they will be particularly larger than the surroundings, so they will be classified as outliers depending on my 2 standard deviation settings. So right now you can apply the filters on the whole image. So you can do that, and it does not cause any specific distortions because, as I said, we specify a threshold, a standard deviation. So anything that's within that 2 standard deviation, the pixels, they won't be modified at all. So that applies to most of the other areas, maybe other than these specific line artifacts here. So even if you apply the whole image, most of the pixels, they're not going to be modified, and only the line artifact here is modified because the threshold arguments to be added up there. And if you are afraid of that, you can even draw a custom region. So for example, let's draw a custom region for now, and you can just select this area because I don't care about other areas, right? So just click this area and double click this box, and you see it's getting fixed. So this means that anything beyond, outside of that region is not going to be modified at all. It only collect the regions within that box. So yeah, you can do a whole image filtering, which is the way I prefer, because it's really you don't have to draw any box at all. So let me go back to the region image. Let's do it again, flatten these, and then we got the so right now I'm gonna fix this one. I think I did make a mistake here. I shouldn't use mask filtering, so it's got some repos there. But I guess it's fine. So let's see whether we can correct all these lines using the median filter. So let's see if it works. So let's continue, click OK, and I want to draw the whole image collection. So now you pop up a new window. So you see 4 images here: the region image, the differential image in binary form, or in the binary form, which means yeah. So basically, when you calculate the difference, what the difference means is once you apply the filters, right, the original image will be transformed to the modified image after filtering, and then if you subtract these 2 images, you got a different image. And if you subtract, then you get some parts of the subtraction is positive, right? Some part of the subtraction is negative. So, and that will be the difference image here, which you have the bright spot will be the positive part, the dark spot, which you can't really see well, will be the negative part. The difference in binary, which basically revert those negative values. So, which means all these bright spot will be the pixels that are different, right? That are modified, whether they are positive modified or negatively modified. So now you can see that the lines in the center mostly get corrected, but I also have some of the corrections are elsewhere, which I don't really want, because those are now useful data. So we want to avoid those situations. What you need to do is you can right click and change. There are several options. So basically you can add another threshold on top of the standard deviation. So as I said, we have a standard deviation, right? Above the 2 standard deviation, those pixels are classified as outliers, and they will get removed. But some of these outliers, right, depending on how far away they are from the mean value, they can be more aggressive, or they can be less aggressive. So then you can fine-tune that threshold. So this is what the threshold here means. If you don't apply any threshold, it basically will take anything outside of the 2 standard deviations outlier. So you can see a lot of pixels that gets modified. So this is where we want a secondary threshold, which is just fine-tune a little bit. So this basically gives a value of the threshold for the outliers. So we have like the minimum threshold for the outliers, and the maximum threshold for the outliers. Well, I understand this is a little bit hard to explain, but I will try to explain well here. But if you still have problems, you can refer to the instruction manual, which I should have more detailed text explanations there. So for this here, we have a lower threshold, which would means that you have basically the outliers, right? So what's the minimum outliers that's beyond the 2 standard deviation, and the higher threshold, which means what's the maximum outlier that's beyond these 2 standard deviation. So then you can basically specify here like how aggressive your outliers would be to be reclassified as a real outlier that needs to be modified. Anything like that's less aggressive, you can exclude them as outliers. So right now I'm going to do is I'm going to write down here, because like 3 nanometer, for example, because I'm sure that specific line artifact it's like several nanometers tall. So let's see what happens. Let's click OK. So you see, right now it only highlights that specific line artifacts there. I might also want to change, because there are some dark lines in that repo, so you can also choose the 3 works fine. You can choose the lower threshold level. So this basically is the I think it's the outlier that's in the opposite direction. I guess I made a mistake in the previous day when I talked about this. So the lower threshold is the negative side. So basically, when you subtract these two, the original image and the modified image, right, you have the positive side, right? So there are outliers that's on the positive side, it's larger than the original image, right? There are outliers that's lower than the original image. So that the larger than the the original image will be classified as the higher threshold. The lower than the original image will be classified as the lowest threshold. So to correct for those dark lines, you have to use the lower threshold. So right now I'm going to use, let's say this one. See how it goes. Apparently it does something, but apparently it's mostly correcting for useful data, but not those lines. I don't think they're corrected at all. So I think that's a mistake. I guess this won't work well. So for now, I'm only going to correct for the higher threshold, which is the line artifacts there. Yes, I think that's so once you have done that, you just close this window. So you see that that artifact gets corrected, but we still have these lines. Well, I mean, you can do a flattening. They just uncheck the mask box. That should take care of that. Those issues there. Right now we still have a bright line because of the flattening thing. So you can use mask flattening, as I did show you before. You can just use the medium filter again. So this time, still use the whole image. Right. Yeah, the lines is included, so you can change this, just fixing that line. For example, let's say 2, maybe, yeah, 2 is fine. I just want to know a bit. Yeah, I don't think it goes too well here. Let's see. 1.5. Well, there are things to take care of the line mostly. Maybe I can do it a little bit more aggressive. Yeah. So that's so the number that I show you right now, 1 nanometer. That's basically the 1 nanometer above the 2 standard deviation. It's not 1 nanometer above the of the image, right? It's the 1 nanometer above the standard deviation. So right, so that's the 1 nanometer above the standard deviations. That's why most of the protein, they're not extruded by only the lines. They are really high. The other one that's going to be get corrected. So I'm going to click this, so you see that should be gone. Yeah, so I don't think that's this may not be the best demonstration there, but typically you only, because I made a mistake in between. So yeah, typically this should be pretty much straightforward. All you need to do is to do a flattening without a mask track, and from there you can either do a mask flattening and then flatten again. That should correct the problem I just showed you earlier. Or you can do a medium filter here and just click OK and click whole image and then close the box, and that should take care of everything. So see. Okay, so this is how to correct for line artifacts. And the other way to do that is if we have a lot of line artifacts. So like if there's a specific area, let's say above these on this area where mouse circle. So if these area are very volatile and you don't want them at all, you can basically crop the image and just completely exclude the top area. So what you do is you can resize the image. Just right click the image and click resize. And then you can drag a box, and I say I don't only want this area, I don't want any else anywhere else. So just double click this area, and you can choose whether to crop this one image or click all images, assuming they are of the same size. So I'm not sure whether they are the same size or not right now, so I just crop this one image. Just click this image. So basically only analyze, the image I cropped. The image is cropped, and then you only analyzing this specific area of the image. So that's one. So yeah. So we also have other analysis other than the median filter. You can also filter by the linear filter and the Gaussian filter. And what they mean, is reading instruction manual. And also you can do the standard deviation, entropy, and the range analysis. They are basically the same kind of tools. You can regard them as filters, but they can also provide you measurements. I classify them in the measurement panel because I think they will be more useful for measurements rather than filters. So what basically they are the filtering tools. They use neighborhood method, and they calculate using the neighborhood. They calculate this like standard deviation, the entropy, and stuff like that in the range. Because you cannot calculate using a single, you cannot calculate standard deviation only use a single pixel. You have to use a neighborhood, right? And you can specify, click the specify neighborhood. Usually, a standard deviation we use a box area, like 7x7 square box area. So it's sort of like filtering, but yes. So to show you here how to measure standard deviation, so you can choose a square box, 7x7 pixel. You can choose any of your size and just click OK. And the same thing, like whether you want to analyze the standard deviation of the whole image, whether you want to analyze a specific area. So let's say the whole image there. Because we are not doing filtering, you can choose a threshold. We don't, because we just want to calculate standard deviation. Just OK. So now you have a new image channel which is called modified height trace, and this one will be the image after applying the standard deviation calculation. So right now it's basically a standard deviation map that's created out of the 7x7 square box filtering. So to see the values of a specific pixel, to see the standard deviation at a specific spot, you just move your mouse there. If you already checked the pixel info box, then this black box will show you the x and y and the value of the standard deviation, which is right now here is like 4.89 e to the minus 10, and right now the standard deviation, this higher one would be the higher standard deviation. Right now it's 1.28 nanometer standard deviation. And then you can also threshold the standard deviation map. That's pretty useful. So I want to see the standard deviation only above like 2 nanometer. Hopefully there's some. Just write them down. Okay, there's nothing. Then we can just go a bit lower. Yes, we actually see something. So see they are masked by red. It's not quite. Oh yeah, there you go. So like above 1.2 nanometer standard deviation, we have several spots there. So this is not the typical roughness measurements that you use in the other software, which gives you basically in the other software you drag a box and it gives you numbers for you, right? The average the value of within the box, standard deviation within the box. In this software, instead of you can still drag a box, right? When you click standard deviation, you can still drag a box on say 7 there. And you can still draw a custom region there. Yeah, so this is basically you can still drag a box, and now you're asking yourself what's the standard deviation within that box. So right now you just place a mouse in the center of the box, which is with the same value that's given by the other software. But the advantage of this software right now is you can obtain standard deviation everywhere inside the spot, not just in the center. Well, all you have to do is to read the the values within this black box or from the thresholding with the red colored area. So that's how you read the roughness parameters. Yeah. Okay, so now we cover the flatten, and apparently I just did a 0 out of flatten, but let's see. Let's go back to this flatten. Maybe let's see. Yeah, let's go back to this one, and so let's see. Let's do an auto thresholding, auto masking. So as you see, the mask will tell you what order you want to flatten the image. The 0 order is just to make them level, to be roughly the same level, so that you can see better what kind of approach you should finally, ultimately take to make the image truly flat. So right now the image is still not flat. As you see that from the threshold, the top area is higher than the lower area. So so apparently we need some more flattening procedures. So what I would do is I probably would do I do our first 0 flattening first. I don't think it's 0 flattening right now. So yes, let's do a 0 auto flattening. So yeah, let's just go down. So the 0 auto is always the first step, but we want to do more. So right now, as you see that the surface kind of warped, so it's higher, and the two sides, like on the left side and the right side, especially higher than the right side. So you cannot do a linear flattening, which only fixes linear surface. This means the surface is kind of quadratic. There's a curvature, it's warping in the center. So you have to use secondary order or third order flattening, which you can choose from this drop box here. You can also do a x direction flattening or y direction flattening. So in this case, you can do a y direction because it's linear in the y direction. So there's no warping in the y direction, but it's only warping in the x direction. So the two ways you can do flattening here. You can either use a y direction flatten at at the first order or 0 order, and that should take care of everything. So you can do that. Just click flatten. So you see it's mostly flattened. So how I say that is because the surface is almost randomly masked, which means they're almost flattened. So if they're not randomly masked, you will see the mask area center at some specific region in the spot, but it's not the case. So the y flattening looks well, and let's try the x flattening with second order. So let's go back to the regional. So the first always the auto flattening in the x direction, non-masked, and click flatten. And now we can do a x direction flattening. Actually, you can do a mask flattening. The mask flattening is is basically, if you want to preserve precision, this is the automated way you want to do it, because when you're flattening, you only want to flatten the surface, right? You don't want to flatten your DNA molecules, because the DNA molecule, protein molecules, they are basically outliers compared to the surface. If you don't use the mask flattening, if you don't exclude them, they basically will screw up your flattening parameters, and it will make your surface basically a little higher and lower, so now it's exactly zeroed. So if you want your surface to be zeroed, basically for calibration purpose, especially if you want to calculate their volumes for the protein DNA complex, you have to get the surface to 0 level. So you have to use mask flattening. Basically, it excludes the protein and DNA from the flattening procedures. So right now, as I showed you earlier, that the surface is kind of warped in the x direction, as you can see here. So to do a masked flattening, you want to check the mask here, but you want to exclude your protein DNA molecules, but you don't want to exclude the surface, because the surface needs to be fixed. It are not supposed to be excluded, so you have to raise the mask level. So until that the surface is not masked, but the protein DNA complex are masked, then you check the mask flattening, because we know it's warped. You can use second order flattening, and then you can just click flatten. So what this means is you flatten the image using the data that's not masked, which basically includes all the surface, right? And but the protein DNA, they are excluded because we already checked the mask, which means they are excluded. So right now let's see how well it does. Just lower the threshold level. If the noise, see right now it's pretty randomly distributed, there's no warping on the surface, that means we did a good job on the flattening procedure. Okay, so in addition to flatten, you can also do a plane fit, which is slightly different. To flatten, basically, is do a line-wise fitting. Basically, it fits each line of the image to a polynomial equation. So you can use any kind of order of polynomial equation. So use the order and first order to correct linear trend, and use second order to correct nonlinear trend, a third order to correct even higher order of nonlinear trend. But for sometimes you probably want to use plane fit, which basically fit the whole surface into a polynomial surface. You can fit them into a linear surface, or can fit into a high order nonlinear surface. So for this specific image, you can actually use plane fit as well. So for example, let's just repeat the procedure again. Always do a 0 order flatten and uncheck the mask box. So right now I see, so we know the surface is warped, right? Just want to make sure before we do that. Okay, I have to go back to the original height trace. Okay, let's do it again. Yeah, so we know the surface right now, so you see it's warped, and right, so you can use a plane fit just to fit to a second degree surface. So you can also use mask as well. So you can do a mask plane fit is image matrix. You can also do a non-mask. In this case, I can do a mask. Just why not? So make sure when you do the mask flattening of plane fit, make sure that the surface is included, right? The protein DNA, your actual, the molecules of interest, they are excluded. Okay, that's how you before you use any mask. That's the golden standard. So right now I can do a plane fit. Just click the plane fit button. You can specify some parameters here, but plane fit, because the surface fit is doing two-dimensional fit, you can fit both x direction and y direction. So just click plane fit, and it asks you for the specific orders. Right now I can use first order in y and the second order in x. That seems to describe the surface well. So just click OK, and so you should finish this plane fit. Right now it's finished. So you get a new modified channel there. It's I'm not sure which one it is. Right now it's trace. Okay, I think it's trace. So you see it's pretty flat. You can use the mask to lower the threshold to check whether it's flattened or not. There you go. You see it's pretty flattened. So the plane fit works well. And you can also do a detrend, which if you have a section line and you just want to flatten that profile line, this is not a good example because it's already flattened. So let's go back to the original image. Yes, this one. Let's flatten this again. Let's just do this channel again. So make sure it's in that specific spot where the surface is warped, right? So this line profile should be warped as well. So you see here, the line here, you see it's kind of warped in the center. And then you can do a detrend function, which basically only fixes this specific. It's not fixing the image, but it's trying to fix the line plot here, the section line here. So you can do a, you can also do a mask, detrend as well. So, but here I just use a secondary order x direction detrend. So I check the result. So right now you see it's warped, right? Let's click detrend. Now you see it's pretty flat, so it's fixed the nonlinear trend here. Okay, so this is so much for the image correction, the basics. We also have corrections using Fourier transform. So now this comes to my third example, which is a periodical. Let's just upscale this first. Let's go to another example first. So for this example, you see that there's a lot of periodical noise in this line here. See that line? There's so many noise there. So periodical noise, they can be useful or it can be harmful depending on what kind of application you want to use. If you are categorizing protein crystals or crystal structures, they are periodical, so they are useful data, so you want to keep them, right? But if you just analyze any random molecules, those periodical noise stuff that usually noise, and you don't want them. So in this case, example, we don't want this periodical thing because they are noise. So how to remove them? Now you click the Fourier transform FFT here. It opens the FFT window, and they have the original image. It's pretty much like the filtering image. So you have the original image, the modified image, basically after the filtering, what I call that, which is a reverse FFT, and also differential image. So right now we have the Fourier transform of the original image. So we can see the periodical noise, the most likely high frequency noise, and you can see the specific spots like in these two areas there. So they are those periodical noise, and then we don't want them. So what you can do right now is the FFT graph, the default is all the regions are included, so they are I call it region of interest. I call ROI, short for region of interest. So there are, this periodic noise are included. So that's why there's no difference between the original image and the inverse for the transform. But we want to make a difference. We want to remove those periodic noise. What you can do is you can say draw an inverse region of interest. Basically, we want to mask those regions. We don't want them, and so that's what you do. I think I can do that. Yeah, just click all these lines at the end, just double click, and then double click, and then you basically mask that area, and do the same thing for the other part of this side. Mask this area, and then I think they are the noise. So let's see. Then say that filter. You can also revert the region of interest. You can do a reverse if you only want to keep the noise, right? Instead of removing them. So you can also reset this region of interest if you're not happy with the current joins. You can also draw a region of interest inside the if you inside of the mask area, if you accidentally include some useful data. You gotta adjust the region like opacity if you have difficulty to see them. But right now I'm going to do is I'm going to filter FFT based on my region of interest. We should remove those noise. Let's see. Yes, so you see a difference image. All this noise are included, but none of the other areas. None of your useful data is included, so you only remove the noise. But this looks pretty good, so I'm just confirm the filter and exit. So you see in the mask area, we don't longer see those noise in the center, so this is pretty useful. Right, it looks pretty great. And so this is where, this is the case that you can remove periodic noise using Fourier transform, but you can also use Fourier transform to keep the periodic information, especially in the protein crystal structures. So right now I'm going to show you another image which has those periodical structures. So in this image you see it's pretty periodical, and so you can use Fourier transform in this case. So I do a Fourier transform there. So it basically can remove other information that's not periodical. It can basically do a reverse, right? Only keep the information that's periodical. So this will greatly refine your periodical information, but remove other information that's considered to be noise or just artifacts, right? And this is useful for averaging purpose. So once you remove those non-periodical information, you basically get the average value for your because the structures are periodical, they basically can be averaged, and any information that's not periodical, they're not considered to be typical features of the structure. They're most likely they're just artifacts, right? So what you do is basically draw a inverse region of interest, or a bit, oh, I shouldn't draw that, right? So basically, you want to remove anywhere else it's not periodic. The intensity, what it show you here is the more warm color, which means it's more periodical, the higher intensity, and the cold color, the blue ones, they are the data that you want to remove, right? They are the low frequency noise. They're not periodical. So yeah, you can draw the same thing, drag a box, but apparently I'm not going to do that, so that's a mistake. Just reset the region of interest. So all you want to do is you want to invert the region of interest. I'm going to draw this. Right now everything is masked, so all the data excluded. And I'm going to draw a region of interest, draw outline, and because I only want to include the data that's periodical, and let's see, let's do this. Yeah, I just only want to include the data that's periodical, that's useful, and other information, they are basically other non-periodic information that likely they are not typical to this structure. So we know the structure because if you do this, if you only keep the periodic information, you get an averaged information of your the structures of your sample. So yeah, I'm almost done. I do want to change a few things though, especially these. I probably want to make a new area, but it's fine because you can do them. I don't really see them pretty well. I'm not sure whether I did it right now. Yeah, let's see. Invert. It does seem like yeah. Yeah, well, we'll know what the result will be. It's hard to see the opacity. Maybe I should adjust the opacity for a bit better, let's say 0.8, because I cannot see them clearly. Oh, that looks much better. So invert. Now I don't know which one is excluded, which one is included. I think this is included in the red region is excluded. I don't know, but let's try. Fill the FFT based on outline. I think there you go. So this looks like the red one on the included area and the blue one that is excluded. So you see the noise, the other things that gets excluded, only the periodic information that gets retained. So this is just a simple guide how to use Fourier transform to keep the useful information and remove the unnecessary information. So after you've done the Fourier transform, you can continue to do a cross correlation, which is also provided in image metrics, and then you can continue to average these specific structures by drawing a specific area to basically add them up to get a fine structures of your sample. Alright, so this should I didn't confirm before the transform, so the image doesn't get modified. But if you do want to modify the image, make sure when you track this, confirm filtering and exit. So that will make a new channel called modified channel in this image, and you can get the results and can export them. But right now, I forget that step. I think that's pretty much for image correction. And alright, if you have any questions, just leave me a message in this video. So stay tuned.